All right, let's just jump right into it. When you've got two different scientific theories, how do you decide which one is, well, better? You'd think the answer is obvious, right? The simpler one's gotta be the winner. But it turns out what scientists actually mean by simple is pretty much the exact opposite of what we think.
So let's ask that question directly. What really makes a scientific theory good? What are those qualities that make one idea so much more powerful than another? Before we go on, just think about it for a second. What would your answer be?
Yeah, most of us would probably jump to stuff like this. It's elegant, it's easy to wrap your head around, maybe it doesn't need a boatload of complicated math, this idea of an economy of thought. And look, these all sound great, but in the tough, rigorous world of scientific discovery, they actually miss the mark completely.
The real answer is so much more interesting, and honestly, it's a bit of a mind bender. It's not about being pretty or easy. It's about being, well, aggressive. Even daring.
Okay, so this brings us to the first huge idea here. We have to completely rewire our brains on what the word simple even means. Because in science, simplicity isn't about comfort or ease. It's a measure of risk. It's all about how much a theory is willing to put on the line.
So here it is, the big reveal. In the logic of science, simplicity is the degree of falsifiability. Basically, a theory is simple if it sticks its neck out, if it makes a claim so bold and so precise that it's actually easy for someone to go out and try to prove it wrong. It's all about being vulnerable to the evidence.
Picture it like this. A simple theory is like a perfectly straight, rigid line. You only need 2 points to define the whole thing. If a third data point doesn't fall exactly on that line, boom, your theory is busted, done. Now, a complex theory, that's more like a wiggly, flexible curve. It has so many adjustable parts. You can bend it and twist it to fit almost any data point you throw at it. It's super flexible, yeah, but that's exactly what makes it so weak.
And this whole idea of testability, of sticking its neck out, leads to something really cool. A theory gets its true power not from what it allows to happen, but from everything it says can't happen.
This is a concept scientists call empirical content. Think of it as the theory's hit list. It's the whole set of observations that, if we ever saw one of them, would prove the theory is dead wrong. And here's the thing. The bigger that list of forbidden things is, the more the theory is actually telling us about how the universe really works.
Okay, here's a perfect example. Let's take the statement, all orbits are circles. It's super simple and incredibly bold. It forbids ellipses, it forbids parabolas, any other shape is ruled out. Its empirical content is huge. Now, let's look at a more complex law. All orbits are circles or ellipses. See what happened? By adding that or, you've made the theory safer, sure, but it now forbids less. And that's the paradox. The safer, more complex law actually tells us less about the universe.
And that right there gets to the very heart of what a law of nature is supposed to do. Its job is to put up fences to tell us what can't happen. It's captured in this perfect little phrase, the more they prohibit, the more they say.
So, all of this builds up to this really fantastic paradox at the very center of science. It's a gamble, a constant tug of war between playing it safe and actually saying something useful.
So think back to our orbit examples. Which one do you think is more probable, more likely to be true? The simple, bold one that says only circles, or the more flexible one that allows for circles or ellipses?
And here's the kicker. The simpler, bolder theory is actually less probable. It's less likely to be true. Why? Because it makes such a tight, restrictive claim that the chances of finding just one little piece of data that proves it wrong are way, way higher. It's a huge gamble.
And you see this trade-off everywhere. I can make a statement with 100% probability of being true right now. Tomorrow it will either rain or it won't rain. I can't possibly be wrong. But what if I told you? Absolutely nothing. The knowledge gain is zero. On the other hand, I could make a simple, risky claim. It will rain tomorrow. Now, that is easily testable, but it has a much lower chance of being right. But if it survives, if it turns out to be correct, then we've actually gained real knowledge.
So, if the simple theories are the long shots, the ones most likely to be wrong, why in the world do scientists love them so much? Why take that risk? Well, the answer gets to the very purpose of what science is all about.
Look, science isn't about collecting a bunch of safe, boring, high-probability truths that don't tell us anything new. The whole point is to push the frontiers, to expand what we know. And you can only do that by making big, bold guesses that have a really good chance of being flat out wrong.
So this is kind of the life cycle of a great scientific idea. First, it makes a bold, simple claim.
Because it's so bold, it's really easy to test it, and to test it hard. It has to face what the source calls the fiercest struggle for survival. And you know what? Most theories, they don't make it. They fail. But the few that survive that trial by fire, wow, those are the ones that give us these huge leaps forward in our understanding.
In the end, it all comes back to this one powerful idea, and this quote just says it all. Simple statements are to be prized more highly because they tell us more, because their empirical content is greater, and because they are better testable.
So I want to leave you with a final question to chew on. If the only way to make real progress in science is to choose the bold, simple, and therefore improbable ideas, what does that tell us about learning itself in any part of our lives? Maybe, just maybe, real learning isn't about finding the safe, correct answer. Maybe it's about having the guts to be wrong.